Okay, in this lecture we're going to cover our section 4.2 material on homogeneous differential equations with constant coefficients. So let's consider some nth order linear homogeneous equation that has constant coefficients. So something of the form given in equation 1, where we have a naught times the nth derivative plus a1 times the n minus first derivative, and so on, up through an times y is equal to 0. So we have a homogeneous nth order linear equation, and these a naught, a1 up through an expressions are constants. So our technique to solve this type of equation is very similar to what we saw in chapter 3 for second order homogeneous linear equations with constant coefficients. That is, to solve, we will consider solutions of the form y equals e to the rt power. So let's take a look at this. If y is of the form e to the rt, then our first derivative would be r e to the rt power. The second derivative would be r squared e to the rt power, and so on. And in general, the nth derivative would be given by r to the nth power times e to the rt. So if we substitute these expressions into our differential equation, we have a naught times the nth derivative, which would be r to the n, e to the rt, plus a1 times the n minus 1 derivative, which would be r to the n minus 1, e to the rt, and so on. And then we have a sub n minus 1 times the first derivative, which would be r e to the rt, plus an times y, which was e to the rt, and we need this to equal 0 to be a solution. So we see that from each of these terms we could factor out the exponential e to the rt, leaving us with a naught times r to the nth plus a1 r to the n minus 1, and so on, up through a n minus 1 times r plus a n. And this still needs to equal 0. And since we know the exponential term e to the rt can never equal 0, the only way this equation holds is if this polynomial in parentheses, a naught r to the n, plus a1 r to the n minus 1, and so on, is equal to 0. So by looking for solutions of this exponential form, we can reduce our differential equation to an algebraic equation where we're looking for the roots of this nth degree polynomial. So this equation that we're left with is called the characteristic equation for our differential equation. So just like for second order homogeneous linear equations with constant coefficients, where we had a second degree characteristic polynomial, for an nth degree equation, we have a polynomial of degree n for our characteristic polynomial, and we're looking for the roots of this characteristic polynomial. So just as for the case of second order homogeneous linear equations with constant coefficients, the form of our general solution will depend on the roots of this characteristic equation. So let's discuss the different cases that can arise. Our first case, case 1, would be the case of real distinct roots. So if our characteristic equation has distinct real roots, let's say R1, R2, up through Rn, then a set of linearly independent solutions would be given by e to the R1t, e to the R2t, and so on, up through e to the Rnt. And we know that once we have a set of linearly independent solutions, our general solution is then some linear combination of that fundamental set of solutions. Now our second case, case 2, is the case of complex roots. So if our characteristic equation has complex conjugate roots, let's say of the form alpha plus or minus beta I, which are repeated s times, so if we have a degree 4 or higher characteristic polynomial, we can have complex conjugate roots which may be repeated multiple times. And in this case, linearly independent solutions are given by e to the alpha t cosine beta t, e to the alpha t sine beta t, then t times e to the alpha t cosine beta t, or t times e to the alpha t sine beta t, and so on, up through t raised to the s minus 1, e to the alpha t cosine beta t, and t to the s minus 1, e to the alpha t sine of beta t. And then our third case, case 3, is the case of real repeated roots. So if our characteristic equation has a repeated real root, let's say r equals r1, which is repeated s times, then linearly independent solutions are given by e to the r1t, t e to the r1t, t squared e to the r1t, and so on, up through t to the s minus 1 power, e to the r1t. So we have a way to find these linearly independent solutions. The form of our solutions depends on the roots of our characteristic equation. And we can construct our general solution by taking a linear combination of this set of linearly independent solutions. So let's look at some examples making use of this approach. We see that it's very similar to what we saw in chapter 3. So in this first example, we are asked to find the general solution of the differential equation shown here. We have here a third order linear homogeneous equation with constant coefficients. So our method for solving is to look for solutions of exponential form, y equals e to the rt power, which means that r would satisfy the characteristic equation r cubed minus r squared minus r plus 1 is equal to 0. And we now need to find the roots of this cubic. So to find the roots of this expression, from my first two terms, I could factor out an r squared, which would leave me r minus 1. And then from my last two terms, if I factor out a negative, I would be left with r minus 1. This needs to equal 0. And then we see from here that we have a common factor of r minus 1. So if I factor that out from each term, I'm left with r squared minus 1 is 0. And then that quadratic that I have, r squared minus 1, can be factored as r plus 1 times r minus 1. So we have roots here of r equals -1 and a repeated root of +1. 1 is a repeated root, it has multiplicity 2. So our general solution, y of t, is then given by c1 times e to the -1t plus c2 times e to the 1t plus c3 times t e to the t. So we see that this solution approach is again very similar to what we saw from chapter 3. For higher order equations, we just have a higher degree characteristic polynomial and therefore more roots. So our general solution contains more terms. So let's look at another example. In this next example, we are asked again to find the general solution of this fourth order linear homogeneous equation with constant coefficients. And so our approach here is the same. If we look for solutions of the form y equals e to the rt power, then r satisfies the characteristic equation r to the fourth minus 4r cubed plus 4r squared is equal to 0. And to find my roots, I could again factor this. I noticed that from each term I could factor out an r squared, leaving me with r squared minus 4r plus 4 is 0. And then that quadratic in parentheses can be factored as r minus 2 quantity squared. So I find that my roots are 0, which has multiplicity 2, and 2, which also has multiplicity 2. So in this case of repeated real roots, my general solution, y of t, would have the form c1 times e to the 0 plus c2 times t e to the 0 plus c3 times e to the 2t plus c4 times t e to the 2t. Okay, so let's look at some other examples. In this next example, we have the same sort of problem. We are asked to find the general solution of this differential equation. We have here a sixth order homogeneous linear equation with constant coefficients. And so our approach will be the same. If we look for solutions of the form y equals e to the rt power, then r satisfies the characteristic equation r to the sixth minus 3r to the fourth plus 3r squared minus 1 is equal to 0. And we might recognize these coefficients as the expansion of some factor cubed. So here we have r squared minus 1, quantity cubed, is equal to 0. Or this term r squared minus 1 could be factored as r plus 1 times r minus 1. And since we were cubing that quantity, we have r plus 1 cubed times r minus 1 cubed. And our roots are therefore -1, which has a multiplicity of 3, and +1, which also has multiplicity 3. So again, in this case of repeated real roots, our general solution would have the form c1 e to the -t plus c2 times t e to the negative t plus c3 times t squared e to the negative t, and then plus c4 e to the t plus c5 t e to the t plus c6 times t squared e to the t. So we see here for these higher order equations, we might have a real root which is repeated more than once, say of multiplicity 3 or higher. And then in our next one, we have the same sort of question. We're asked to find the general solution of this fourth degree homogeneous linear equation with constant coefficients. And so our approach is the exact same. If we are looking for solutions of the form y equals e to the rt power, then r satisfies the characteristic equation r to the fourth plus 2r squared plus 1 equals 0. And this can be factored as r squared plus 1 quantity squared is equal to 0. So our roots would be plus or minus I with a multiplicity of 2, since this r squared plus 1 was being squared. So here we have the case of complex conjugate roots, which are repeated. So our general solution in this case would have the form y of t is c1 e to the 0 times cosine of 1t plus c2 e to the 0 times sine of t plus c3 times t cosine t plus c4 times t sine t. So in this case of repeated complex conjugate roots, we take our solutions and we can generate new linearly independent solutions by multiplying by these factors of t out in front. So let's consider an example of one of these higher order linear equations, but paired with a set of initial conditions. So here we are asked to find the solution of this initial value problem, where we have a third order homogeneous linear equation with constant coefficients, and then we have a set of 3 initial conditions involving y, y prime, and y double prime at time 0. And then we're asked to plot the graph of this solution and describe its behavior as t increases. So we know to solve this type of equation, we look for solutions of exponential form, y equals e to the rt power, which results in the characteristic equation r cubed plus r to the first is equal to 0. And this can be factored by factoring out an r, leaving us with r squared plus 1 is 0. And so our roots of this characteristic equation would be 0 and plus or minus I. So we have one real distinct root and a pair of complex conjugate roots. So here our general solution would be of the form y of t is c1 plus c2 times cosine of t plus c3 sine of t. And to solve for my constants, c1, c2, and c3, I need to apply my initial conditions, which involve up through the second derivative of y. So I need to find my first 2 derivatives here. My first derivative of this general solution would be negative c2 sine of t plus c3 cosine of t. And my second derivative, y double prime, would be negative c2 cosine of t minus c3 sine t. So let's apply our set of initial conditions. If we evaluate the general solution y at time 0, we're left with c1 plus c2, and we were given this value must be 0. Y prime of 0 is equal to c3, and we were told this value has to be 1. And then y double prime of 0 leaves us with negative c2, which we were told must be 2. So it follows from my third equation that c2 is negative 2. And from my first equation, since the sum of c1 and c2 is 0, that means that c1 has to be the negative of c2, so that would give us a positive 2. So substituting these expressions back into our general solution, we find that y of t is given by c1, which was 2, plus c2, which was negative 2 times cosine of t, plus c3, which was 1 sine of t. So this is our solution of that initial value problem. And we're asked to plot the graph of the solution, which I've included here in the lecture notes. And then we're asked to describe its behavior as t becomes infinitely large, or as t increases. So here, as t is increasing, we see that our solution y of t, because of the sine and cosine terms, will exhibit oscillations. And since our first term was a constant 2, the oscillations are going to be centered about y equals 2. So we could say that our solution y of t oscillates about the value y equals 2 with a constant amplitude, or a fixed amplitude. So here we don't have increasing or decreasing amplitude for our oscillation, since the real part of those imaginary roots was 0. So again, here we have a value of y equals 2, and our solution is exhibiting oscillations about that constant value. So let's look at one last example. Here we are asked to solve the initial value problem, where we have a fourth order homogeneous linear equation with constant coefficients. And since we have a fourth order equation, we have a set of 4 initial conditions involving y up through the third derivative of y at time 0. And again, here we are asked to plot the graph of that solution and describe its behavior as t approaches infinity. So we know our method for solving this type of equation is to look for solutions of exponential form, y equals e to the rt power, so that r satisfies the characteristic equation r to the fourth minus 4r cubed plus 4r squared is equal to 0. And we see that we could factor out an r squared from each term, leaving us with r squared minus 4r plus 4 is equal to 0. And then that remaining quadratic can be factored as r minus 2 quantity squared, So we find that the roots of this characteristic equation are 0 with multiplicity 2 and 2, which also has multiplicity 2. So our general solution, y of t, has the form c1 plus c2 times t plus c3 e to the 2t plus c4 times t e to the 2t. And to finish out this problem, I need to find my constants, c1 through c4, using the initial conditions. And since my initial conditions involve the third derivative, I need to find my first three derivatives of this general solution. So here our first derivative, y prime, would be given by c2 plus 2c3 e to the 2t plus c4 times, by the product and chain rules, we would have 1 e to the 2t plus 2 times t e to the 2t, or factoring out an e to the 2t, we have the following. And then our second derivative, y double prime, would be 4c3 e to the 2t plus c4 times, again by the product and chain rules, we would have 2 e to the 2t plus 2 plus 4t. So altogether we have 4 plus 4t times e to the 2t. And then for my third derivative, y triple prime, I have 8c3 e to the 2t plus c4 times, once again by the product and chain rules, we would have 4 e to the 2t plus 8t times e to the 2t, leaving us with a total of 12 plus 8t e to the 2t. So once I have my general solution and these first few derivatives, I'm ready to apply my initial conditions. So let's evaluate y at time 0. Substituting 0 into the general solution, we're left with c1 plus c3, which must be negative 2. For y prime at time 0, we're left with c2 plus 2c3 plus c4, which must equal 0. Y double prime at time 0 gives us 4c3 plus 4c4, which has to equal negative 2. And then y triple prime at time 0 gives us 8c3 plus 12c4, which must be equal to 0. So we have here a set of 4 linear equations involving 4 constants, c1 through c4. And there's a number of ways I could go about solving this. So here, when I look at my last 2 equations, I see that they only involve c3 and c4. So I have 2 linear equations involving 2 variables. And so we know how to solve this type of system of equations. There's a number of ways I could go about it. Let's look at this set of second 2 equations here. If I were to consider this system, 4c3 plus 4c4 equals negative 2, and 8c3 plus 12c4 is equal to 0, well, I see that if I were to multiply my first equation by a factor of negative 2, and then add that to my second equation, the c3 terms will cancel. I would have a negative 8c3 plus 8c3, and then a negative 8c4 plus 12c4 leaves me 4c4 is equal to, on the right-hand side, I would have 4 plus 0, or 4, and so it follows that c4 must be 1. And now substituting back into one of my previous equations, I can solve for c3. It follows from my second equation that 8c3 is equal to negative 12c4, and since c4 was 1, that would be negative 12. So c3 is negative 12 over 8, or negative 3/2. So once I have c3 and c4, I can then substitute back into my first two equations for these constants to obtain c1 and c2. So let's take a look. From my first equation, I have c1 is equal to negative 2 minus c3. So that would be negative 2 plus 3/2. So negative 4/2 plus 3/2 leaves me with negative 1/2. And then from my second equation, I find that c2 is equal to negative 2 times c3 plus c4. So negative 2 times c3 would be a positive 3 plus c4, which is 1, leaving me with a value of 3 plus 1, or 4. Oh, excuse me, my c2, when I solved for c2, it was negative 2c3 minus c4. So we have a positive 3 minus 1, or 2 for that constant. And so now substituting these constants back into our general solution, we find that y of t is equal to c1, which was negative 1/2, plus c2, which was 2 times t, plus c3, which is negative 3/2 e to the 2t, plus c4, which was 1 times t e to the 2t. So this is my solution to that initial value problem. And then we were asked to plot this solution and describe its limiting behavior. So here in the notes, I've included the figure. And we see that as t becomes large, from our starting value of negative 2, we see an initial decrease before we start to see exponential growth tending towards positive infinity. And we can see that directly from the solution here. As t becomes large, this last term, t times e to the 2t, is growing more rapidly than any of these previous terms. So that last term dominates our growth. And we see that as t increases, our solution, y of t, will increase towards positive infinity.